Okay, so we just looked at this function here, near 0, and we saw that there was no limit. In fact, we saw that if you approach 0 along two different paths, one it seemed that the value was always 1, and the other it seemed that the value was always -1. And then they showed, although we didn't go through it, that if you approach 0 along a line that passes through 0, mx, then actually the limit will turn out to be this, so it will be dependent on m. And then they say you might suspect, might lead you to think that you can establish the limit by showing that the values of f as x approaches a along straight line paths, if they all the straight line paths all tend towards the same value of L, then you can say that the limit is L. But actually that's not always the case. So just because, even though you can check along, show that like along any path, straight line path to A, you get the same L, that still doesn't mean that along every path, because not every path has to be a straight line path. You could sort of define a path in a different way. They say, although this is certainly good evidence that the limit should be L, it's not conclusive, and they say you can check exercise 3 to find out what can happen. Okay, now to do the same function again, they suggest, how about rewriting this function in terms of polar coordinates. That might somehow make things, we might see things that we don't see so easily right now. So remember that the transformation x equals r cosine theta, y equals r sine theta, and then so somehow we get x is r, so you get this, x squared, you get y squared is this, and you factor out stuff, and you get this equals that. So actually the function in terms of polar coordinates is kind of simpler. It's just the cosine of 2 theta. So we started out with this, but when we write it in terms of r and theta, it just turns out to be this. So that's interesting. Now, I guess we assumed when we did the cancellation here that r is not 0. So this is true when r is not 0. So if we want to check what the limit is as x approaches, as the vector x, or as this approaches this, then we only have to think, let r approach 0. And there's no restriction on theta. But this doesn't even have an r in it. So the limit of this as r approaches 0 is just this, nothing. It's just the same thing. It hasn't changed. So the limit is this. And this shows very clearly that the limit depends on theta. So you get different limits depending on what the angle that you enter, or the angle that of the path that you enter, that you go towards 0 is. So if you're going on theta equals 0, you get 1. If you're going on pi divided by 4, you get something else, and so on. And so this also shows us that the limit won't exist, because there's not just one answer to the limit question. Okay, another example, they say, suppose we want to do this one as it goes to 0, 0. They say let's use polar coordinates on this one as well. So we take this, we get that. Now if cosine theta is between, now cosine theta will always be between -1 and 1. So that means that you can do this, I guess, but you're subtracting r squared here. I don't know, what are they doing here? So I guess what? So the biggest that this can be is 1, And the biggest that this can be is 1, so the biggest that the second term can be is r squared. That's 1 plus r squared there. And this can be negative 1, and this can be negative 1. So it could be negative r squared minus 1. So we can say that. So we said that this is equal to that, which is, this part is here, so the only difference here is r is in there. So if we multiply, so f is with the r inside, so we multiply both sides by r, and that we can say f is bounded by that. Now we can see that as r goes to 0, both this and this go to 0, because r is forcing them both to go to 0. So now we can now we've seen that for this function, the limit does exist, and it's equal to 0. So that was interesting that we could use polar coordinates. Like, probably would have been hard to get an answer if we hadn't used polar coordinates. But with polar coordinates, it wasn't too hard to show that the limit exists and the limit is equal to 0. Okay, next they say one of the biggest drawbacks of our definition of limits that we have, which is back at 2.2, is that it's not useful for determining the value of a limit. You must already have a candidate in order to use definition 2.2. Let's check what is 2.2. So this is it, but it just shows, it just says if you have a candidate like L, you can check whether it actually is. But it doesn't show you like how to find L, so you know, it's kind of, it's not very useful. You're not likely to get, I mean, in general, we can't guess what L is. So she says one of the biggest drawbacks is that it's not useful. You already have to have a candidate L, candidate limit, in mind, and also must be prepared to confront some delicate work with inequalities. So the results that follow, which are proved later, can be useful to find limits. So let's, this is, first of all, theorem 2.4, which is called the uniqueness of limits. So it says if a limit exists, it's unique. What does that mean? That means if there is a limit, there's only one of them at a particular a. So if you know that the limit of f of x equals L, and you know that the limit of f of x equals m, both as x goes to a, x goes to a, then they have to be the same. You can't have two different limits at the same a for f. And the next thing are these properties which can help quite a bit in finding limits. So let's suppose that we have two functions, f and g, both are vector valued, and they both go from Rn to Rm. And suppose that we have some let's see, we have f and g, small f and small g, which are scalar valued, going from Rn to R, and let k be a scalar. So we're going to just use these in the statements 1 through 4. So the first one says that if you have f and you know its limit is L at A, and g, and you know its limit is m at A, so they both have to be at the same place A, then you can say what's the limit of the new function f plus g at A, and it's just going to be L plus m. So let's see if they give an example of that. That's weird. Okay, this is kind of strange, but because they're talking about the limit of, this should be in here, since this is a vector of xy, we should have both x and y, but this just says x equals a, and this says y equals b. So then they say you can use this, you can say this is, I'm not quite sure what this means. I guess what this means is if you have, this is the function, it's actually a function of x and y, but they're saying if you just have a function, your function of x and y is just equal to x, and you do this limit, you get a, you just get x is going to a, x comma y is going to a comma b, so x is going to a, so you get this, and if your function is just equal to y, then this limit is b. This is a little bit weird, but okay. From these facts it follows from theorem 2.5, parts 1, 2, and 3. Okay, we haven't gotten there yet, so let's keep going. If the limit as x goes to a of capital F is L, then you can ask, what about k, some scalar times f? It will just be KL. So these have to be proved using that rigorous definition that we just saw before. Okay, another one rather, is if f is a scalar function, then the limit as x goes to a, if that's equal to L, and g, the limit is m, then the limit of f times g, remember both of these are multivariate functions, they have vectors as inputs, is L times m. Okay, so these are probably going to be useful in doing some problems later. So, okay, and the last one is what happens if you do f divided by g and you get L over m, as long as neither as long as g is not 0 for any x in x, and also that the limit of g of x as x approaches a is not 0. Then you get this. Okay, that's a little bit surprising, although she says nothing is surprising. So they're exactly the same as the corresponding results for scalar valued functions of a single variable. So from basic calculus, the same set of theorems. Moreover, 2.5 renders the evaluation of many limits relatively straightforward. So if you want to do this one, then this says that you can break it up like this, to the limit of the first part plus the limit of the second part plus the limit of the third part, like this. And why can you do that? Because of part 1 of theorem 2.5, which is the one that says you can take f plus g and make it, and get the limit of f plus g, or I'm sorry, if you have f and g, then you can say the limit of f plus g is equal to L plus m. You can break them up into pieces. And then by parts 2 and 3, well, by parts 2 and 3, now we have this, and then this is the limit of x squared. That can be written as the limit of x quantity squared. That's because of part number 3 here, this thing. And number 3 here. And this one is also number 3, and this one is number 3, and this is number 2 actually also, because we can take the constant out like that. Okay, and so now we see, and also then from knowing these, we know now that we can do this and get just the x value, so just a here. So this is a squared, and this is 2ab, and this is b cubed, so you get this. But basically what we can see is that when we're doing the limit of a polynomial, this is a polynomial in 2 variables, we can basically just replace the x and y's by this. So it makes it easy to do limits of polynomials. You don't have to convert it to polar coordinates. You don't have to do a lot of algebra. You just drop in the values of a and b. In fact, more generally, a polynomial in two variables is defined like this. So basically, you get terms like this from this. So, so this is a double summation. I don't know if we've talked about double summation. The way double summation works is, so you look at the outside one, the first one. This is like the outside one, and you set k equal to 0. So that means set this k to 0, this k to 0. Okay, so you get c sub 0 l, x to the 0, y to the l. Okay, with k set to be 0, then you do this thing. So that means L is supposed to go from 0 to D. So first you do L equals 0, so you get 0, 0 for these two subscripts. You get 0, 0 for these two exponents. And then you let L equal 1, and you get something else, and you add. So you do the one with 0, and then the one with 1, and then the one with 2, and you go all the way up to 2, and you add all of these together. That's only, now you've only done it when k equals 1. Now you have to let, k equals 0. Now you have to let k equal 1 and do the same thing again. Then you have to let k equal 2 and do the same thing again. And then keep going until you get to D. Okay, and that's the form for a polynomial in two variables. So here's just one example of a polynomial in two. Here's just one example of a polynomial in two variables. Okay. Okay. So we can show, and they're going to show in this example, that to find the limit of a polynomial of two variables, generally speaking, the limit of a polynomial, generally speaking, is you can just put the limit inside. So they explain how they're using the different parts of the theorem to do this, but you can do that, then you can do this. So basically what it says is, if you have x comma y going to AB in your general polynomial, to get the limit, you can just replace x and y in the polynomial with a and b. Okay? So you don't really have to do any limits. You just put in the values. Okay? Now we get a little bit more complicated than that here. So now suppose we have, this was a polynomial for just two variables, and here we're talking about a polynomial in n variables. So we have a polynomial in n variables. This is the definition. This really means, like here we had just two variables, so we had two sigmas. So this really means that you're going to have n sigma signs in here to work with. So it's kind of messy. Okay, but here's an example of a polynomial from R4 to R. So R4, there's 4 elements in here. It's 4 variables as input variables. So you got this one, and then this one, and this one. So this is obviously, this is a polynomial, and it's obviously in 4 variables. There's 4 variables here. You can see 1, 2, 3, 4. So there's at least those in here, and then there's 3 and 4, so that's already here. So anyway, it's a polynomial in 4 variables. So this is generally what a polynomial in n variables, what we mean by it. And the limit, still, when you're doing a limit like this, you can just put in the values a1, a2, a3 for x1, x2, x3, and so on. Okay, let's see. Here we use some of the stuff we used before, plus the theorem, part 4 of the theorem, which deals with division, because we need division here, and they get an answer. Let's not go through that. And then they say that those theorems above don't always work, because here, if you're going x going to 0, 0, this bottom part is 0. The theorem said you're not allowed to have that equal to 0 and still use the theorem. So that means we can't use the theorem, so not so easy then. So they start playing around. They say, what happens if you look at as x goes to 0 along this axis? We get 1, supposedly, while on this axis we get -1. So already we know that the limit doesn't exist at 0 as x approaches 0, as the vector x approaches the vector 0. Okay, now we talked before, recently, about the component functions, the scalar valued component functions. So you have a function f going from Rn to Rm. They're going to be m component functions for each element in the output. So it turns out that if you want to know the limit of f, you can just concentrate on the component functions, or you can just view it as its component functions. So remember that if f is like this, then f can be rewritten like this. So we have m component functions. So theorem 2.6 says that if f goes from Rn to Rm, then the limit of f equals L, where L, of course, has to have m components because it has to be in Rm. But L is, L1 is the, so Li or L1 is the limit as x goes to a of the first component function, f1, and L2 is the limit of the second component function, and so on. So if you want to do limits on a vector valued function, you can break it down into m limits of the m component functions, the m scalar valued component functions. So that might make it easier, or it might not. So as an example of this function, of this theorem, suppose that we have, let's take a function from Rn to Rm, and specifically, let's suppose that we have a matrix, an m by n matrix. So m rows and n columns, and we're going to multiply that by a vector on the right. So if this has n columns, this vector has to have n rows. So that's what they have here. And since this has m columns, the output is going to be m columns as well, and just one, oh, I said that wrong, sorry. Since this has m rows, the output is also going to have m rows, and and only one column. The output is only going to have one column, so it's going to be an m by 1, or it's going to be a vector in Rm, which is what we want. And so each of the rows is going to give us the component function for the corresponding element in our answer vector in Rm. I don't know if I said that very well. But anyway, this is the first component function, and this is the second component function. Remember, we have to have m of them, and this will give us m of them. This is the mth component function. But now, using theorem 2.6, we can figure out what the limit of this is as x goes to b by just figuring out what the limit of each one of these is as x goes to b. But we already did this. These are polynomial. This is like so actually our earliest example. These are linear functions in x, in the vector x, which has n elements in it. So anyway, these are linear functions in the vector x, and we already did this before. Let's go back and see where that was. So this was here. This was pretty long ago, actually. This was like before we talked about these balls and boundaries and all that. Before that, we did this, that the limit of a linear function in x, this is like a linear function in the vector x, you can just dump in the various components of b into there. So that's what we're facing now. That's what we're facing now in this problem, because these are, we want to do the limit of this as x goes to a, but we can write it in terms of its component functions here. But each of these component functions is a linear function of x, so we can just drop in what x1 is, what x2 is, because we're doing that here. We're going to do as x goes to b, so in other words, we could just drop in b1 for this, the first component of b, and b2 for this, the second component for b, and the same thing for all of these, the same b1, b2, and so on. So each component function is going to look like this. So so the first row is going to be a11, a12, a1n, and the second row is going to be a21. So the component functions, there are m of them, and the first subscript is going to change from component function to component function. So this one is a1 something, this one is a2 something, and the last one is am something. So the first subscript is going to be the one that changes. So f sub I, so the ith component function is going to be this, the I is going to be the first subscript here, and the first subscript here, and so on. Okay, so with that, we can just drop in the b's, and we get that for the ith component function. So now we've basically done it. So writing this out, we can write this equals this. We're mentioning the component functions, and then we can just put in the b's, so we get this, and we can turn that upside down, sort of like this, write it as a vertical vector like this. But that is exactly what we mean by AB, actually. If you figure out what AB means, you'll get exactly this. So what we've shown is that the limit, the limit of, if f is given by ax, the limit as x goes to b is ab. So that seems a little bit almost obvious, but it's not obvious. And we had to do it by breaking it down into component functions and then we end up seeing that what we got is exactly AB. Okay, next we will do continuous functions and then get some theorems about that. And that will be the end of our limits, and we'll start on the derivatives.